Okay, so as I was saying, no matter how long the tube is or how collimated your beam comes out of the laser, there's still chances, that some beam's going to hit right at the edge and scatter. So, while you can know statistically how likely, it might be very unlikely for it to go out. That long tube will make it very unlikely. But some still will, so you won't know any spot that a photon absolutely cannot go unless you use quantum mechanics, because then you can have kind of these interference patterns, and that makes high probability and low probability. So there are some it won't go because of the zero probability, but not absolute zero, so it still holds in general. Okay, so the thing that quantum mechanics explains, it's practical. It's not the two-slit experiment as an oddity itself, but it had ramifications. The solution so far offered for it turned out to be really productive in a lot of areas. And this is like earlier in the other video where this is just reminding you, I think, of things you're somewhat familiar with, maybe not thinking about the connection or why they demonstrate a certain thing, but I mean, not that you won't get your own conclusion to things, but to a certain degree, the parts kind of make sense. So it starts with, why does copper burn blue? You can think, well, who cares? Or alchemists have known it burned blue for a long time, and what color other things burned as. But quantum mechanics explains why. Okay, you could say, oh, well, somebody else could explain it. Well, no, nobody else. There is no other mathematical formulation that can calculate the exact color of blue, and not only for copper, but for every chemical, including colors we've never seen before, that the alchemists didn't see before, including colors that can't be seen by the naked eye, and radio wavelengths and other wavelengths. And the importance of this is, for example, how much do you believe in the importance of this, and the idea that certain chemicals burn with certain colors? Because I'm curious if you believe that the sun is made of hydrogen, because this is how we know the sun is made of hydrogen. This is how we know that most stars are made of a tremendous amount of hydrogen, and that being the most abundant thing in the universe. Now, what we really know is that we see colors when we break stars into rainbows and can see the individual colors, each one related to an individual chemical. If you have enough resolution, sometimes these lines are close enough together that they're blurred together, but if you have enough resolution, each chemical has its own transition, like a fingerprint. And that's what we really know, is that the colors are the colors of hydrogen. When you burn hydrogen on Earth, you get those colors, both visible colors, but more importantly, the X-ray colors. These are all colors, X-ray, microwave, microwave being, centimeters, millimeters size, long wavelength light, radio, meter long light wavelengths. And this really ends up explaining everything, because we see energy interchange by collecting the photons and knowing that these photons relate to certain state changes that mathematically only quantum mechanics describes. And we have learned a lot of things about the rest of the universe. We learned that we thought there was nuclear power fusion in the sun and various things like that. We still don't know. We know it's possible in the sun. Of course, it's not going to be that useful if we have to start a sun, because we don't want a sun burning on Earth. Maybe a sun in a cup would be useful. Maybe it's possible, maybe not. But we know in principle that fusion is possible. At least if fusion means this phenomena that seems to be explained as fusion, because it emits the same kind of energy that you would expect. It's a different kind of fire. Quantum mechanics explains, all of those, because even in the chemical processes, the reason those molecules emit that light is because of the quantum effects. And the main thing, too, is in an atom, and the difference in quantum theory and maybe an older, more classical electrical theory, if there isn't even really such a thing, because I would say it wasn't that established before a more modern view came along to explain it. The electron is not a little speck at all, a little particle in orbit around that nucleus. It's a little bubble, it's a little quantum bubble. And it's sort of quasi, nobody's looking at it, doesn't have an interaction, but it's behaving in this little bubble. And if another electron gets in there, it combines There could be multiple shells. It's like a multiple layered little bubble that could be there. And and it's because these bubbles, you can have a bubble around one and another atom, and then the bubble becomes like, you know, hourglass shaped or something, you can imagine it, and it's holding both of those things together in a little pocket, and that's holding molecules together, these shared electrons. And that's the only way we've explained why molecules hold together, and exactly the energy that it takes to break those bonds are calculated. And by exactly, I simply mean to the billionth place, you know. And yeah, we'll go further. I mean, and it'll probably deviate at some point. I believe it'll deviate. There'll be some mathematical crisis and it'll deviate, and we'll have to add our theory. Or for that matter, this is really a theory of electromagnetics. We're trying to bring it together with um, uh, you know, gravity and just the element of mass and stuff, and there's some crossover already, but really this is the theory of electromagnetics, and it might be that there's another field in the universe besides electromagnetics that explains, you know, why things work the way they do in the universe. But I really like you to explain this issue of that the only reason we know the sun is made of hydrogen, if you believe that, is because quantum mechanics is explaining to us that. And you could say, oh no, but trial and error, I can burn hydrogen here and well, but that's not quite how it works, because you have to know where to look when you're finding needles in the haystack, little thin lines of radio waves or something. So the point is that in terms of having an explanation, like you say, hey, someone should work out the math. They have worked out the math, and this explains it. You know, in math of it being scattered particles with no quantum wave part of the equation, no wave dimension of the equation, that has been tried, and it does not work out. You can just do it. I'm not saying take my word for faith for it, but the point is that math will not explain why copper burns in blue. Um, and help us see, you know, stars thousands of millions of light years away, what's going on there. That if the chemicals react the same way they do here on Earth, then we can figure out, and it's all because of these state transitions. And there's only theory that's explained that to us. And the reason we figured that out, and the reason we know why integrated circuits work, and the reason we know why they're starting to fail at their current level of miniaturization, it's all because of quantum effects. And it has a lot to do with the with wavelength, because, you know, when they talk about making the circuits too close together, because and then there's a quantum problem where the currents will just tunnel spontaneously over because it's too close. That's related to the wires being closer than the wavelength of the energy going in the wire. That's what promotes that. It has very much to do with these thresholds of, it's like analogous to the slit size and the distance between the slits. These systems are very delicate that when you're going to make these quantum systems, you're going to play that. You're going to have a radiation of a certain frequency, and you're going to know exactly how far apart they are, and you're going to take advantage of weird channeling and weird effects that happen with wave mathematics. I mean, in Maxwell's equations, not in, you know, kinetic collisions. And it's not that there's not good stuff about kinetic collision and classical mechanics, but it really is limited to the macroscope, whereas this wave functionality works at all levels. On the other hand, it's way too complicated and too much trouble for what detail you get out of it at our levels. But people need to remember, it is, you know, molecules and why biology works. If you could be a molecule and have eyes and ears and look at what's going on, you'd be looking right at quantum effects. That's what holds you together. You know, that's the sinew, that's the tissue that holds you together as a molecule, is like electron clouds stretched out in these weird bubbly shapes that are coursing around in a kind of an orbit, but it's this bubble surrounding kind of an orbit. So kind of a plasma-y thing. Again, the final thing I just want to say is, looks like I don't have too much time, but the final thing is that, remember, it's not so uncommon sense to say a photon could hit two slits at once. Because if I said you were in a wave, there was a break wall, and it had two holes in it, and I said one thing hit two slits at once, I mean hit the two gaps at once, you'd have to ask me what kind of thing, because if it was a boat, then that would not make sense. But if it was a wave, it makes sense, because obviously the wave would come up and hit both of these gaps at once, and have gone through both at once, because that's the kind of thing. It's a distributed big thing. All right, cheers.